Phillips, Bethel Baptist, the Brevard Jewish Community, First United Methodist, St. Timothy's United Methodist, and the Unitarian Universalists of Transylvania County have collaborated to produce a fall speakers series with presentations focusing on climate change and its impact on the local environment. 3 weeks ago, we heard from Dr. Jennifer Frick-Rubert concerning the effects of climate change on the local biodiversity. During her presentation, she spoke about the unsettling increase in droughts, punctuated by violent, heavy rains. How prophetic. 2 days after her presentation, Western North Carolina was hit with the remnants of Hurricane Helene, a storm which barely registered on the radar a week before. The torrential rains from the storm caused flooding of biblical proportions and devastating widespread damage, including significant loss of life. Our hearts bleed for those whose lives were lost or forever impacted by this horrific storm. In tonight's presentation, Dr. Jake Hagedorn will try to bring some hope to the table in his presentation, Mitigating Climate Change, Using Science to Transform Uncertainty into Progress. He will analyze successful climate mitigation strategies already in place and investigate new, innovative approaches to addressing an uncertain future. Dr. Hagedorn is an assistant professor of environmental science at UNC Asheville. He received his BS in environmental science at UNC Asheville, MS in geoscience at Pennsylvania State University, and Ph.D. in environmental science from University of Maryland Center for Environmental Science. He teaches soil science, agriculture, and energy courses at UNC Asheville. His research focuses on assessing how farm management practices impact water, soil, and air quality. Please join me in welcoming Dr. Jake Hagedorn.
Thank you, Bob, for that introduction. The other thing I'll say is that I am a soil biogeochemist, so that is my training. The title of my talk is Mitigating Climate Change, Using Science to Transform Uncertainty into Progress. And so I see many familiar faces in the crowd, so I just want to give you a little sense of my journey that Bob touched on, just so that you know where we know each other from. So I grew up in Brevard, elementary, middle school, and high school. I went to UNC Asheville for my bachelor's in environmental science. I played soccer there. I then accompanied my wife on a Fulbright to teach English in Sri Lanka for a year. After that, I went to Penn State to get a master's in geoscience, University of Maryland Center of Environmental Science for a Ph.D. in environmental science. Then I taught for a year at Warren Wilson College. And now I've landed my dream job at UNC Asheville, where I've been for about 3 to 4 years and hope to be for the rest of my career. Okay, so the focus of this talk is on climate change. So I'd like to start by kind of describe the science of climate change. And some of this might be review. That's good if it is, okay? So what is climate change? It's essentially just the energy balance of Earth. And that can change over time. There are natural factors, non-human factors that influence the climate on Earth, and then there are human factors that influence the climate on Earth. So we can measure those to figure out what is driving modern climate change. So if we look at this, this is observed temperature since about 1880 to about 2014. So these are the observed temperatures we've seen. Anything above this center line is hotter, lower is colder. So you've seen, since about 1950, we've seen higher temperatures over time. So what factors match that? So we can look at orbital natural change, so changes to how we tilt, how we wobble, how we orbit the sun. Those don't really match with the observed temperature change we've seen. How about the solar? The sun is getting bigger, it's getting more intense, it's emitting more energy. But over this period of time, does it match what we see in our observed temperature change? No. How about volcanic emissions? That's a natural, non-human impact on climate. Again, we've measured that. Sometimes it warms, sometimes it cools the climate. But again, that doesn't match the observed temperature change that we've seen. So we can factor in all of these natural changes which have influenced the climate on Earth in the past. We see that they combined don't really match the observed changes we've seen. So now let's think about some human factors, all right? And so one of those, so one of those is land use change. So think about deforestation for the purpose of agriculture, okay? Has land use impacted climate? Yes, but again, it doesn't match the observed change. What about ozone? Many of you have probably heard of the ozone hole, particularly 30 or 40 years ago, the ozone hole in the stratosphere, right? It's a big problem. Ozone has impacted our climate, raised the temperature, but relatively minor compared to the observed changes that we've measured. What about aerosols? These are things like dust, particulate matter in the air from wildfires. That actually cools our climate. It's a human impact that cools our climate. We need to know that. Then we have greenhouse gases, things like carbon dioxide, methane. That kind of matches the observed trends we've seen in temperature. So when we add all of those human factors together, we can see the land use, the ozone, the aerosols, which actually have a cooling effect, combined with the greenhouse gases. You're going to see that all of those together, in the next slide, is going to pretty closely match the observed changes we've seen since 1880. So this is the strong evidence we have that human factors are dominating modern climate change. Natural factors affected past climate change on Earth, but human factors are affecting the modern. So, I mentioned greenhouse gases. What is the greenhouse gas effect? So greenhouse gases are just molecules in the atmosphere. We mentioned a couple already: carbon dioxide, methane, nitrous oxide, the laughing gas you might get at the dentist. Okay? Most of the energy on Earth comes from the sun. So the sun's radiation comes to the Earth's surface, gets absorbed by the Earth's surface, and then the Earth radiates that out as infrared radiation. When that infrared radiation from the surface of the Earth gets to those greenhouse gas molecules, they get excited and they start to vibrate. And when they vibrate and get excited, they trap some of that energy in the lower atmosphere. More energy in the lower atmosphere means higher temperatures. So that's what the greenhouse gas effect is. And the greenhouse gas effect has an outsized impact on the Earth's energy. So I want everyone to take a deep breath for a moment. Breathe in. And out. Okay, so the air that you breathe, what was it composed of? Well, you can see here that most of it is dinitrogen, which is not a greenhouse gas. 78% of our atmosphere is dinitrogen, not a greenhouse gas. So you breathe in mostly nitrogen. The next largest fraction is oxygen. About 21% of our atmosphere is oxygen. We need that, right? We're happy that there's oxygen there. A relatively small fraction, less than 1% of our atmosphere, is greenhouse gases. Okay? So you can look at this fraction here. CO2 is 0.0407% of our atmosphere. So this is important because without greenhouse gas emissions, life probably wouldn't exist on Earth. It would be too cold. We do need to trap some energy for life. However, if we trap too much, we're also going to have a negative impact on life. And so the reason I show you this is because I want you to see that CO2 and greenhouse gases are a very small fraction of our atmosphere. But that means that we can impact it. All right? And so changes to relatively small quantities can have large impacts. I want you to think about that as we go through the rest of this talk. All right. Now, I wouldn't be a biogeochemist if I didn't show you a carbon cycle, okay? And the reason this is important is because we talked about greenhouse gases like CO2 and methane. Those are just forms of carbon. And carbon is spread throughout the earth in a variety of different places, okay? So on this graphic, I want you to look at the circles and the arrows. And the circles are sources and sinks of carbon, where carbon is accumulating in different places on Earth. The arrows are where carbon is moving to or from, all right? And the important things I want you to take away here are, here you can see these are fossil carbon reserves or sources. This is our emissions of those fossil sources into the atmosphere. Now, we don't just have emissions into the atmosphere, we also get carbon dioxide and greenhouse gases taken out of the atmosphere, which is good. And where does that happen? This light green arrow is vegetation and soil taking carbon out of our atmosphere. Some of the carbon that we put in. The other thing I want you to look at is this arrow here, which is atmospheric carbon moving into the ocean. So the ocean is a very large circle, very large sink for carbon dioxide and greenhouse gases, and we have a flow of that into the ocean. So the whole purpose of the carbon cycle is just understand where are these movements for better understanding where can we have an impact and where can we make the biggest difference. So where has all this anthropogenic or human-caused carbon gone? All right. So this graphic shows you parts per million, or the concentration of carbon in the atmosphere. And the reference here is in 1850, we had 285 parts per million. Over time, we've been burning fossil fuels and emitting greenhouse gases into the atmosphere. Since 1850, our coal has added about 105 parts per million. Oil 79, gas 36, cement, others. Land use change has added CO2 into the atmosphere. So if those were the only things, we just thought about things going into the atmosphere, we would be expecting to have about 600 parts per million. Thankfully, we don't. And the reason we can be thankful is land and the ocean. They are taking up about half of the carbon that we've emitted into the atmosphere has been taken up by land and ocean. And that's really important because if you think about the climate impacts we're currently experiencing, we could expect those to be amplified by about 50% if the land and the ocean didn't take it up. Okay? So we're thankful for the land and the ocean. And now we currently have about 416 parts per million of carbon dioxide in our atmosphere. So what's our current trajectory? Where are we going? So this graph shows global CO2 emissions. And the red dot represents where we are currently, okay? And all the different colors you see on the graph represent different scenarios of where we could go, okay? So there are some scenarios at the top where we continue to increase CO2 emissions drastically. And then there are others where, right here, we pretty quickly reduce CO2 emissions. But right now, we're on track for the orange and the yellow, where we will likely continue to increase our global CO2 emissions, and we'll peak somewhere around 2040, 2050, and then we'll start to decrease into 2100. The problem is that we need to get to net zero here fast, all right? That's the best mitigation strategy for climate change, is to get there fast. So another way of kind of thinking about this and framing this, I like this graphic, is how does this affect temperature? Okay, so we have the CO2 emissions, but how does this affect temperature? So since 1750, you can see the blue lines are cooler temperatures. The red lines, more intensely red, the higher the temperature. And you can see on the right side of the screen, there are about 5 different climate projection scenarios evaluated here. Just a little bit of terminology. Note in the upper right that the curved arrow is peaking our emissions. So we're peaking and then going down. And we have halving our emissions, so we half the peak. And then we get to net zero. So let's look at a very optimistic scenario, okay? Which is the lower one, okay? On the bottom right here. So let's say we were to peak our emissions now. And let's say we were to half those emissions by 2030, and we got to net zero by 2060. Look at the red there. Even if we did that now, we are locked in to inevitable temperature increase, even if we did that now. All right? However, if you compare that to the intermediate option in the middle, where we peak in 2030 and we don't half until 2080, you can see the intensity of the red is really deep. Okay? So the now looks pretty good. Especially the lower option looks pretty good compared to the intermediate. All right? But I like this again because the color. You can see that we're going to live on an Earth that has warmer temperatures than have ever existed since 1750, and that will continue. Okay? So, why does this increasing temperature matter? Increasing temperature is going to increase the probability and intensity of extreme weather events. We're currently in one. We just got through Hurricane Helene. That was an extreme weather event. Okay? So more extreme weather events is going to be more loss of life. It's going to be more property and community damage. It's going to be more uncertainty in global trade, agriculture, and energy markets. To kind of give you a theoretical framework to think about this probability, you can look at this graph here. On the y-axis, we have the annual chance of an event. On the x-axis, we have temperature from cooler to warmer. Warmer being more intense, a more intense extreme weather event. The blue line represents, let's say, a 1950s hurricane. Okay? So a pre-industrial climate hurricane represented by this dot. And let's say that was a Cat 2, a Category 2 hurricane. Okay? What we would expect in the current and future climate is the red line. So we would expect that this Cat 2 hurricane, if we move vertically, will become more probable. So instead of happening once every 5 years, it now happens once every 3 years. And moving horizontally on this, we're going to increase the intensity. So instead of a Category 2 hurricane of 1950, it's now going to be a Category 3. And if we move diagonally, we're going to see now a Category 3 that occurs more frequently. So that's the future that is coming, and it's already here. We've already been dealing with it. We will continue to deal with that. All right. Okay. This is not new news, necessarily. NOAA, the National Oceanic Atmospheric Administration, has been measuring this since about 1980. So this graph shows you the number of billion-dollar disaster events since 1980. The different colors on this graph represent different extreme weather events like drought or freezing or tropical cyclones, hurricanes, or flooding, or wildfires. Okay? What you can see here is that since 1980, and again, this controls for inflation change and what $1 billion is. But since 1980, you can see beginning in about 2010, we start to see an increase in billion-dollar event, extreme weather events. Okay? This is driven by climate change. All right? Specifically, you see a big increase in the green. And that green is severe storms. Okay, so just make note of that. Severe storms are kind of the big increase from 2010. All right? Some of y'all will see Katrina, Ivan, Francis in there between 2004, 2005, 2006, around that period of time. But you can see from now until 2020, we see a very high amount of billion-dollar disaster events. So what will future temperature feel like? All right. So I want to give you all an example of an app that a colleague of mine developed at the University of Maryland. For those that are technologically savvy, okay, this is a QR code. And if you want to take a picture of that QR code, you can then open up the app's website and go to the website, all right? You don't have to, just if you want to. So what I'm going to show you is kind of anticipation, a prediction of what the temperature will feel like in 60 years, okay? So in this app, what you can do, and I have the QR code on every single one of my examples, so you can continue to take a picture. So you go to this app, and you can say, let's go to Asheville. I want to know, what is Asheville going to feel like in 60 years? And you can do this for any city around the world. And Asheville is, if you click on Asheville, Asheville is going to experience, it says, an increase in temperature, and it's going to be wetter. And it's going to feel like Rome, Georgia. Okay. Now, so that gives you a little bit of a climate analog of what a place is going to feel like somewhere that you know. Okay. Now, some of you might be thinking, Rome, Georgia, maybe that's not that bad of a climate difference. Like, you know, Rome, like Georgia, might be a fine place. So let's look at a different place. Charlotte. Charlotte in 60 years is going to feel like Houston. Okay. Let's look at another one, Jacksonville. So Jacksonville will feel, Florida will feel like central Mexico. Okay. So this is pretty much what we're locked in for. We know this is going to happen, and we want to take mitigation steps to just keep it at this and not make it worse. Okay? So, now I want to start thinking about the main part of the talk, which is mitigation strategies, so that we don't get worse than what that app was predicting. All right, so two terms I want to define first. Mitigation versus adaptation. Both important, but different. Mitigation is reducing, either by emitting less or capturing more, the amount of greenhouse gases in the atmosphere to limit climate change severity. So examples of mitigation are consuming less fossil fuels, having alternative fuel resources, increasing renewable energy production, changing transportation, regrowing forests, increasing energy efficiency in a variety of different sectors. Adaptation, on the other hand, is learning to live with the climate change that already exists and has been set in motion. Okay? Now, this includes things like infrastructure improvements, or making crop modifications to grow crops that do better, maybe drier, warmer environments. Early warning systems for extreme weather events, and in some cases, managed retreat. So we think about sea level rise, we might be talking about managed retreat of populations. Now, it is important to note that these two terms are definitely connected to one another. You can think about how some mitigation measures would definitely impact how much adaptation we have to do. The more mitigation we do now, the less adaptation we have to do. The other way around, we have some adaptation strategies that will actually help to reduce greenhouse gas emissions as well. So these are connected. The main purpose, the main goal of this talk, though, is to think about mitigation. All right, adaptation is extremely important. However, the main purpose of this talk is mitigation. So, to set some framework to think about mitigation, this is a carbon management hierarchy. Some of y'all are probably looking at this going, I see reduce. This makes me think about reduce, reuse, recycle. Right? You're right, totally right. Okay. Just a few different words from a carbon perspective. The first thing and the most important thing is for us to avoid emissions for mitigation. Then reduce them, then replace them, then offset them. So you can think about this like driving. Your first option would be don't drive, right? your second option, reduce, would be if I'm going to drive a car that gets a high miles per gallon. I want less emissions that way. And then if I want to have a bigger impact, I would replace that with an electric vehicle that has even less carbon emissions associated with it. And if I wanted to do even better, even though it's more difficult, I would offset the amount of energy that it takes to charge my car, which probably came from carbon emissions. Okay? So that just gives you a little sense of thinking about where did the mitigation examples that I show you fall on this triangle. Now, before talking about some specific mitigation examples, here's a snapshot of the current greenhouse gas emissions in the United States from 1990 to 2022. And a few things to note here. First, beginning in about 2007, which is right here, you start to see a decline in greenhouse gas emissions. Great, that's awesome, right? That's good. We've seen a decline since 2007. Another thing to note is which sources are the largest. So in this case, the blue, the pink, and the green, industry, electricity generation, and transportation, are the biggest impacts for greenhouse gases. Not residential or agriculture, important, but not the biggest emitters of greenhouse gas emissions. The last thing to note is the thickness of the lines. So note here that for the pink, the electricity generation, particularly in 2007, right here, is thicker than it is now. So what has driven that decrease in total greenhouse gas emissions is a change in electricity generation and a reduction in greenhouse gas emissions via electricity generation. So we're going to come back to that. Keep that in your mind. How are we doing compared to the rest of the world, you might ask? Well, this is annual fossil CO2 emissions per capita, per person. All right? And you can see this is from 1960 to 2022. We are decreasing. We're right here. We are decreasing, same as the last graph. However, we still have the highest carbon emissions per capita of anyone else in the world. Okay? So we have the furthest to go if our goal is 0. All right? All right, so now let's examine a few climate mitigation strategies that are already implemented and that have been working. Okay, the first one, declining coal. Okay, this is a successful mitigation example. Coal has been in decline. This graph, you can see the different colors of U.S. electricity generation by different energy sources. The brown is coal, the blue is natural gas, and the green are renewables. And you can see that in the year 2000, you start to see a big, or that 2005, you see a big decline in coal. Okay? And, but I want you to note that the top of the graph kind of plateaus. So that means that we've leveled off in our electricity generation, which is good. But if we've leveled off and coal has declined, that means something has replaced coal. And what is that? Natural gas. And that's from hydraulic fracturing or fracking. Okay? A lot to do in New York, Pennsylvania, Williston Basin, a variety of different places in the U.S., but the increase of fracking. Now, this is important because it is important to know that coal is an extremely, it emits about twice as much carbon as natural gas does when it's burned. Okay? So natural gas is a cleaner fuel, but it's important to note that it is not a clean fuel. A clean fuel is renewables, solar, wind, even nuclear. It can be a clean fuel. However, natural gas is cleaner than coal. And that is actually what has largely driven that decline in greenhouse gas emissions. All right, the next successful example, increasing renewables. These renewables also happen to be CO2 free. And we're talking about mitigating emissions, so that's our goal. So we see that the primary renewable energy for us has been hydroelectric since about the 1970s. And we kind of stayed steady with hydroelectric. And we'll continue, we'll probably decrease a little bit. But in about 2005, you start to see an explosion driven by large-scale, utility-scale projects. Not necessarily individuals putting solar on their home. We're talking about utilities, governments, corporations, doing big projects is primarily what has driven this increase. Okay, so why has that increase in solar and wind happened? Well, this graph proves that cost went down. Okay, so if you look at photovoltaics, which are solar, you do onshore and offshore wind, from about 2000 to 2020, you can see that you just had a significant drop in the cost to implement those technologies, to produce electricity from those technologies. So much so that now they are currently cheaper than fossil fuels. So it takes less money to produce electricity from solar and wind than it does from fossil fuels. So in our economy, if it's cheaper to produce it from those sources, we're going to do it. All right? And we have. So you see this market adoption rate has pretty much exponentially increased for those technologies. Where has this happened? Texas, Iowa, California. That's where the wind and the solar are happening. All right. North Carolina is in there. It's in the mix, but not as much as Texas, Iowa, and California. Okay. Another successful mitigation strategy example is the Inflation Reduction Act, passed in 2021 by Congress. It was partially derived from the Green New Deal, which you might have heard of. And it includes lots of funding for a variety of different programs, primarily in the form of tax credits. So it takes the approach of using the carrot, not the stick, right, to promote more clean energy projects. One thing to note here is that majority of these tax credits are going towards, again, large organizations, corporations, utilities to implement clean energy projects. Now, a fraction of that, specifically the individual clean energy incentives, about $22 billion, that actually goes to residential money. So that could be for things like installing heat pumps, or efficient water heaters, or some solar PV systems, or biomass stoves. You can actually get a tax credit for implementing those at your home, and a small fraction of that bill contributes to that. Additionally, this is where a lot of the EV tax credit money comes from. So the electric vehicle, the $7,500 off for many vehicles comes from this bill as well. And so when we think about how much of an impact the Inflation Reduction Act is having on climate mitigation, we can see that it seeks to expedite the decline that is already happening in greenhouse gas emissions. So the red here shows scenarios where we didn't pass the IRA, the Inflation Reduction Act. In the blue is the different scenarios with the Inflation Reduction Act in place. So what you can see is there's a modest decrease relative to no IRA in how quickly we are decreasing emissions on average based on a variety of different scenarios. So that's good. However, it doesn't get us to net zero, which is where we need to get to. Okay, so those are some examples of some large-scale mitigation strategies that are currently in place and are effective at reducing emissions, but maybe not fast enough. And so we got to think about how can we get to net zero faster. And this is where we're going to talk about future mitigation options. So first I want to frame this, okay? Many people might talk about future mitigation as we might have some technological breakthrough or some silver bullet solution that'll solve this. Some people say nuclear fusion, or widespread change in human diet, or widespread adoption of regenerative agriculture. Those are all great things. However, probably not realistic for the next 20, 30 years. okay, which is when you need to make the biggest difference. So it's more likely that we're going to need to be doing small incremental changes using existing technology in a variety of different sectors. Okay? Small changes to governments, small changes to corporations, making a big impact. All right? And the other thing I want to address here is just individual versus structural change. Most of this talk has been about structural change, big picture, large-scale change to have a big impact. Now, individual decisions are important, but they don't have the impact that large scale does. Okay? So just keep that in mind. Structural change will have a bigger impact. So that's what we should be pushing for. This graph I use every semester with my students. And it essentially is another way to kind of frame how we think about future mitigation strategies. So one example that I use as a soil scientist is soil carbon sequestration. What that means is, are there different agricultural techniques that we can use to try to take carbon out of the atmosphere, put it in the soil, and keep it in the soil? And we have estimates of the maximum biophysical potential there is for that. We can do that up to this point. This is the potential. However, we have to buffer or temper that measurement with what is physically or maybe technologically possible, right? We also have to buffer that with what is economically achievable. And then we also have to buffer that with what is politically and socially achievable. And these are just the realities of any mitigation strategy going into the future. And so ultimately we end up at some potential that is further from the maximum and closer to the minimum. So that's something we have to consider in every one of the solutions that we propose. All right? So, with achievability in mind, considering the economic, political, and technological achievability, the International Panel on Climate Change, scientists of multiple disciplines, have put together, essentially, opportunities for scaling climate action for mitigation. Okay? And so I'm going to walk you through these graphics real quick. So here you can see mitigation options listed here. Okay? And then you see these bars next to these mitigation options. And the length of those bars, essentially, what is their potential to actually decrease emissions? And then you have colors in there. That's considering what is the cost to do that. Blue is super cheap. Yellow is pretty cheap. And we get more expensive the closer we get to red. So if we think about future mitigation options, this first one I'm going to show you is talking about solar and wind within the energy supply sector. Okay? So you can see that a bunch of scientists have run a bunch of models, and essentially they've determined that solar and wind could have the greatest impact on reducing carbon emissions. And it's cheap. Let's do that one. Let's keep doing that one. One thing I do want to note here is that these graphics do include adaptation, knowing that that's an important piece of this as well. And there's a relationship between mitigation and adaptation. I'm not going to get into that in too much detail. I'd be happy to give you this resource and you can look into that, but know that they do consider that. Okay, so future mitigation option 1, keep going with solar and wind. It's cheap and it can make a big difference. Next one, agriculture. So let's look at the agricultural sector. The most impactful mitigation options are reducing conversion of natural ecosystems, so less deforestation. And then the next one is carbon sequestration. Oh, soil science, right? That's the second most important thing for agriculture. Awesome. However, look at the color of the bar graph.
Very expensive.
More expensive compared to solar and wind. Doesn't mean we don't do them, just knowing that that is probably going to be lower on the list than solar and wind. Okay? But again, soil carbon sequestration, we're trying to take the carbon out of the atmosphere, put it in the soil, keep it in the soil. And there are different agricultural practices that do that better than others. Now, to give you a little further detail about agriculture, because this is getting into kind of what I do, what I research, what I study. Think about different agricultural techniques that could contribute to climate mitigation. So this graph shows the area of practice of adoption. All right, smaller area, larger area. The x-axis shows the greenhouse gas reduction or removal rate. So more removal rate, less. What I love about this is that look over here. Right here, you have the highest removal rate of carbon dioxide in a super small area. Okay? That's an example of making a big impact in a small area. Okay? So, what is this dye? Anyone know what restore histosols means? Okay, so histosols are soils, and they're wetland soils. So this is all about restoring wetlands. Wetlands are extremely good at holding carbon and keeping it there. And so if we can restore wetlands, then we're going to have a big impact in a small area. How can we do that in agriculture? Well, in the Midwest and in around the world, historically we've drained wetlands to make room for arable agricultural land. What we could consider doing is re-wetting some of those systems, maybe even seasonally. Maybe not while the crops are growing, but maybe when the crops aren't growing, re-wetting them to help carbon stay in that system. Okay. The last thing I want to show you is cropland management. So I spent a lot of my dissertation on the eastern shore of Maryland, looking at different cropland management techniques and how they influence greenhouse gas emissions. So things like fertilizer efficiency, things like conservation tillage, things like increased cover crops, all of those decrease greenhouse gases going into the atmosphere. And so if we can do more of that, we're going to see an impact on greenhouse gases. All right, so the last mitigation option I wanted to talk about is infrastructure and transportation. So here you see the mitigation options. The most important ones are having more efficient buildings, fuel-efficient vehicles, and electric vehicles. Okay? So here, efficient buildings, darker colors, pretty high cost. Fuel-efficient vehicles, pretty cheap. Why? We already have them. We already have them. Okay? Electric vehicles, in this study, they did not have enough data to make a color for this. But I'm sure in future iterations they will. So this is for infrastructure and transportation. All right. So let's think about getting to net zero. Now I know you're thinking that the mitigation strategies that I proposed are in many ways just a continuation and intensification of what we're already doing. And you're right. But to me, that's a really good thing, right? That means that we don't have to wait around for a silver bullet. We don't have to wait around for a technological change or reinvent the wheel. Rather, we just have to enact the things we already know and do. You might also be saying, but Jake, you said we need to get to net zero, and the Inflation Reduction Act gets us closer, but doesn't get us all the way there. You're right. It doesn't get us there fast enough. So where is the hope? How can we get to net zero? So a group from Berkeley put together a study that examined how we can do that, doing the things we are already doing. All right? And so here you can see that if we take these 8 actions by 2030, we will be able to achieve net zero carbon emissions by 2050. It's not the best outlook in that temperature different scenarios, but it's close. It's close. And so you can see we need to increase solar and wind by 3.5 times. We need to eliminate most electricity generation from coal. We're well on our way. Let's keep going. Maintain current natural gas generating capacity. Okay, so plateau natural gas. Increase zero emission vehicle sales to 50%. increase sales share of building heat pumps to 50%. All new buildings and appliances meet strict energy efficiency goals. Now, there are 2 more on this list, and I haven't talked about these, and I'm not going to. I'll be happy to take questions if you want to about them, but they are talking about carbon capture, sequestration, and then transmission of that carbon. I'm going to ask you to kind of ignore those for a little bit. Those are important, but not necessarily the purpose of this talk. And I want you to focus on the first 6, and the reason they're the first 6 is because they're most important, okay? These are things we're already doing that we just need to continue to do. So my takeaway here is that we already know what to do. We're already doing it to some capacity. We just have to have the will and courage to do it more. So I'm going to give y'all a little breakout time. This is what I do with my students all the time. A little breakout group brainstorm. 5 minutes. That's it. 5 minutes. All right? So I want y'all to get together, talk with your seatmates, people you're sitting next to. Given this figure, what can Brevard do, the city, to mitigate climate change? Given these are the things that need to be done. So I want you to brainstorm with each other. So take 5 minutes. I'm going to come around and talk to you. Take 5 minutes to talk to each other. What are different ways Brevard could help facilitate this? Wrap up our brief conversations. I obviously didn't get around to everyone. That wasn't necessarily the intent. But I hope you got to talk a little bit about, and I'd be happy to talk after the ideas that you have. Some of the people I did talk to have some great ideas. So I'm going to finish up here. And thank you all for your quick discussion. As we close this evening, I do want to take a step back a little bit and acknowledge that this talk was highly focused on carbon emissions, which is crucial for understanding climate mitigation. That's the reason for it. However, it is important to not have carbon tunnel vision for the future as we transition to a more sustainable future. Carbon emissions are just one piece of our future that is connected to a variety of other important issues. Things like inequality, education, poverty. They're all equally, if not more important, and they're all influenced by carbon emissions. Okay? So it's going to require interdisciplinary collaboration from scientists, from people, to evaluate how can we make progress on all of these issues simultaneously. And to kind of drive that point home just a little bit further, I want to show you a report that many of my colleagues have contributed to from the United Nations, where they've defined 17 sustainable development goals globally. Okay? And essentially, I'm only showing you some of them, but I just want you to see that a lot of scientists have gotten together to figure out how are we doing on all of these goals. And so we'll pick one. This is the goal of no poverty. And in 2023, we have made moderate progress of eradicating extreme poverty, but we have limited or no progress kind of looking forward right now. So that might be an area that we need to focus on. And then you can get down here to climate action, okay? And there are a variety of others: zero hunger, industry and infrastructure. One of them is increased access to mobile networks, which we struggled with Aline, right? However, that is doing pretty good. We're getting close to our goal for that globally. And we're making substantial progress getting there. So that's good. Now for climate action from a global perspective, I mostly told you about the US perspective. From a global perspective, we've got a ways to go. All right? We've got a ways to go on reducing greenhouse gas emissions. Okay. So I hope the one thing that you've taken away from this talk is that a silver bullet solution is not on the horizon. Okay? Future mitigation strategies to get to net zero are essentially just implementing strategies that are already technologically and economically feasible. There is hope in knowing that we just have to intensify what we're already doing to get to net zero. That said, getting to net zero is going to take at least another decade, which means that we are going to have a certain amount of temperature and climate change impacts that are inevitable, that are locked in, and that will require us to adapt. So to conclude, I'd like to take a moment to further connect these ideas to our shared humanity via philosophy and religion. So I'm going to read a passage from a book written by my late granddad-in-law, Ed Barrett, husband of Sue Barrett. So this is a passage from his book, Mapping Tomorrow's Planet. Like a butterfly struggling to cast off the remnants of its cocoon, tomorrow's planet is already a living and beautiful reality in our midst, a global village of interconnected and shared humanity. Supporting us through nature and history, the divine reality in which we live and move and have our being is also challenging us to expand this unity, to abandon the national idolatries and political obscenities which still cling to us, while furthering the liberty and rights of individuals and caring for the natural world. The responsibilities and potential for calamities are enormous, but good religion has always been a tricky business, a risky business, as the story of Abraham makes clear, involving ventures into an unknown and unmapped tomorrow. Jesus reportedly said that you cannot put new wine in old wineskins. The church must be willing to be something other than the old, dry, cracked, and leaky jugs of the past. New wine is awaiting us, and a new world, if we are willing to walk with courage and commitment into tomorrow's planet. So, thank you.